Okay, am I on? Yeah, cool. Thank you, Marco. Thanks for the introduction. Thanks for coming. Yeah, as Marco just said, I want to give you an overview of our current understanding of SYK physics. But before getting there, let me start with a bit of pep talk, trying to motivate the story. So I think we can all agree that coping with the complexity of many degree of freedom quantum systems is one of the big challenges in quant math or even in physics at large. And from my perspective, I think the sources of complexity are threefold. First of all, we are dealing with many correlated degrees of freedom. Yeah? Second, in such systems, interactions or even the presence of external randomness often act as sources that break integrability and render the dynamics partially, if not fully, chaotic. And then very important, the third one, we are doing quantum systems, which means that we are dealing with an exponential complexity growth in the extension of the system. And that third one is really a sucker. I mean, if you think of, like here, this cartoon of 10 to the 8 compound spin chain, and compare that to today's computers that can, I don't know, solve 20, 30 or what, and that will not change unless we manage to build a quantum computer. Yeah? So on that background, I think it is remarkable when in 2015 the SYK model in its modern incarnation came up, a model that on the one hand displays almost the full extent of quantum chaos, many-body quantum correlations, and so on. And on the other hand, it's just simple enough to be analytically solvable to a large degree so that you can actually, within this realm, do parameter-free comparisons between numerics and analytics and really have a microcosm to explore many-body quantum correlation phenomena to an extent which I don't think is available in any other system. So that's what makes, I mean, is really a great asset which we have there. And on that basis, let me introduce to you, I mean, if you don't know it, I mean, the definition of SYK models. The SYK model in its modern form stands in the tradition of a somewhat larger class of models which one may call random interaction models. These are very simple model Hamiltonians where you take a large but not thermodynamically large number of quantum particles, mostly fermions but not necessarily, and let them talk to each other. Everybody talks to everybody via an interaction matrix elements about which you assume very little information. And you can hardwire this into the model by drawing them from a random distribution, but there are other ways available. Yeah? So these are the random interaction models, and there are at least 4, depending on the counting, 5 incarnations of these models over history. And these are actually instructive to know, so let me briefly guide you through this. So models of this type surfaced first in nuclear physics, as always in this game in the early 70s, where people tried to inject chaos into the, or model chaos in the physics of complex nuclei in manners not quite as phenomenological as brute force random matrix theory, but really by starting from some random two-body interactions. Now, at the time, computers were slow, analytic progress was considered impossible, and this kind of modeling never really took off to, I mean, became not a mass development. Yeah? But the buzzword that goes with it is embedded random matrix ensembles, if you want to know. So that was the first incarnation. 20 years later, the models were rediscovered, now in the context of quant math. Sachdev-Ye-Kitaev, that's the S and Y in SYK. They were studying some kind of correlated random magnetic materials. They didn't know about the earlier developments in nuclear physics. But they contributed one important insight, namely they realized that there are some conformal symmetries present in these systems, and we will get to that later on. And quite a bit later, 2015, came the most recent incarnation of the model by Kitaev, SYK now. The point here is that Kitaev proposed to look at a Majorana version of this Hamiltonian. So instead of dealing with complex fermions, now we deal with real fermions. Here's the Majorana-Clifford algebra. Kitaev's motivation for introducing this model was holography. I mean, he proposed this as a 0+1 quantum mechanical boundary of a two-dimensional ADS bulk. But from a different perspective, and that will be my perspective today, there is a huge consequence in using Majoranas. These Majoranas are a lot more user-friendly. than fermions. So they're kind of nominally simpler, and that has to do with the simplicity of this algebra. And it is this model where we can make really clean analytic progress. I should say that now in hindsight we understand that the physics of the complex fermion models is not so different in many ways, but that was the one which really served as a kind of platform to work with. And to close the definition, I mean, in this context here, we really do consider now Gaussian distributed random, static random interaction matrix elements, so quench disorder if you want. And there is an energy scale here that sets the ultraviolet scale in the problem. Yeah? So this is the Hamiltonian I want to consider the following. Now, these were 3 incarnations. Let me briefly mention number 4. It's kind of interesting. A little bit later, Witten and Klebanov and Tarnopolsky proposed a non-random version of this model. I mean, so here you consider something that looks complicated, but it's kind of a miniature tensor network, which you have here. No randomness. And I'm just flashing this to highlight that the physics of this Hamiltonian here is pretty much identical to that of the random Hamiltonian. So randomness is not really essential in this business. What is essential is that the interaction Hamiltonian induces a very high level of entanglement. Yeah? So that, I mean, it's obvious more or less from the definition. There is incarnation number 5 due to Wickman, who argues that this model is equivalent to a set of Russian potatoes. And so thick, disordered Russian potatoes, and I leave it to the audience as an exercise to figure out where that connection might come from. And if you care, you can submit answers later on. But anyway, that's just not so essential for us. We will look at the Kitaev version, yeah, of my runner. And the way now the talk is organized, this being a chaotic system, it is imperative to distinguish between dynamics at short time scales and at long times. I'll make precise what I mean by that in a sec, and we will look at them separately in the following. I will focus on, if you want, on foundational aspects of the physics, but still I will try to give you some glimpse of applications and discuss a bit of where all this is useful in condensed matter and in chaos. Not so much holography. Okay, so what is that about timescales? The thing is that if you deal with any kind of many-body system, I mean, supposedly chaotic, you should distinguish at least minimal set of 2 fundamental timescales. Timescales polynomial in the number of degrees of freedom you're working with. These are usually the timescales separating, as, if you want, semi-classical short-time regime from a strong quantum fluctuation-dominated regime at longer times. So that's one. And then you can enter a time machine and go to all the way much, much longer timescales of the dimension, of the order of the dimension of the Hilbert space. And that is these timescales are reciprocal in the sense of uncertainty to the energy scales comparable to the many-body level spacing. So here you really probe fine structures of the many-body spectra and wave function and God knows what. Yeah? Now, SYK makes no exceptions. Physics is very different in these regimes, and at short time scales, keywords, I mean, characterizing the physics include exponential instabilities indicating chaos. These days, it's fashionable to call this scrambling. Very importantly, there is a symmetry at work, which we'll see that the physics here is really, I mean, strongly dominated by a conformal symmetry and its spontaneous breaking, which we will discuss. And as a consequence, we observe strong collective quantum fluctuations which dominate this regime here. And everything is very universal and nice. At large time scales, the model approaches the regime of quantum ergodicity, becomes maximally chaotic, maximally mixing, and all these keywords. We observe universal spectral correlations, and there is another symmetry at work, which I will explain what it is. You can call it a causal symmetry, and it's breaking. Nobody knows how these regimes here connect. This is an open problem in the field. But what is nice is that we have analytic theories approaching the problem like a pincer from both ends. Yeah? So there is a formalism called G sigma theory. I'll explain what that is, which works best at shortish time scales and gets more tricky here. And conversely, there is a replica nonlinear sigma model which works perfectly well at asymptotically long scales, but gets more tricky as we go to shorter scales. So you can attack from both sides, and this is what gives us a lot of leverage. And there's a clean cut. I discuss both regimes in turn. Yeah? And please do interrupt me anytime if anything is not clear. Yeah? Okay, so first, short timescales. Let's try to understand the physics of of this system. And, well, what we do is we stare again at the Hamiltonian, ask what we should do with it. And the thing to emphasize now is that there is a large number of particles, and everybody talks to everybody. So this is crying out to be mean field treated in some way. Yeah? So like Sherrington, Kirkpatrick, or whatever. I mean, it wants to be mean fielded. And you can do this, run this approach coming from different angles. And perhaps the simplest one is just straightforward diagrammatic perturbation theory. Now then you can ask perturbation theory around what? I mean, you have just this interaction. There is no other energy scale to compare with. But let's just do, something blindsided and do naive perturbation theory around zero Hamiltonian. Yeah? And see what. And so what I mean by that is the following. You pick an observable to, for example, like the Majorana two-point function. Yeah? That would be an Majorana I at imaginary time tau and j at tau prime. To zeroth order, if you think of the action of a problem, the propagator of this is 1 over d by d tau. It's not like 1 over energy plus zeroth order Hamiltonian, because there is no zeroth order non-interacting Hamiltonian. It's just 1 over d by d tau. That thing is bloody stupid, but the only thing it tells us is that these are fermions, so they have fermionic statistics. Okay, so now we do perturbation theory around this limit in the interaction. At first order in the interaction, we get nothing because these guys are Gaussian distributed with zero mean. So we have to go to second order. And at second order, you have here 4 Majorana, so you have an interaction vertex here and here. You have a disorder average, which correlates them. And what you then get is this object here, which in the jargon of the field is called a melon. So these are the melon diagrams, which in this business are popular. And what you can do now is you can push on in this way and melanize to a higher order. So you sum diagrams of this kind of structure, you go higher and higher. You do not tolerate crossing interaction lines because for each crossing line you can probably smell it. You would have to pay with a factor 1 over n. So you do a self-consistent summation of these melonic diagrams, and people call these field theories emerging from here melonic field theories. But it's conceptually all very similar to self-consistent Born or RPA approximation, only that now we are summing diagrams of this hierarchy. And this series can be self-consistently summed. Yeah, you do the usual thing. You write a fat propagator, naked propagator plus this. So this is a resummation of this series. And this equation here is actually simple enough to be solved. So it's solvable. You can solve it, and that gives us quite a bit of insight into the model. So let's see how that goes. Remember how you solve a beta side beta equation or any self-consistent equation you like. You rearrange the equation such that you solve for the full green function in this case. Then there is this naked melon, which plays the role of a self-energy. And now comes one approximation you do in the solution of this problem. You see the characteristic energy scale here is J, is the interaction scale. But you're interested in low energy physics, so you declare that this d by d tau is small, and to begin with zeros, negligible compared to the self-energy. Later on we will relax this, but to begin with you just cross out this guy. And if you do that, if you cross out this time derivative, the equations g equals 1 over sigma, and sigma being 3g's, they become algebraic equations. So you now have an algebraic set of equations, and you can solve them in no time, just by dimensional analysis or whatever. And what you get is this. These are the results now for the green function in this approximation. The most important point here is that the green function, seen as an argument of 2 time arguments, is 1 over square root of time. Yeah, 1 over square root of time. Telling you that the fermion, the green function is like fermion, 2 fermions. The fermion carries dimension time to the 1/4. And that is very non-Fermi liquid-like. So this indicates that we are totally, there is no Fermi liquid physics here, no Landau paradigm. No surprise, because we don't have a zeroth order interaction. There is no Fermi surface. It's just this, so no quasi-particles interpretation. Yeah? So that's one important message we learn here from this equation. And that's about it, what we learn. So far so good. This is as far as you go at this level. Now, I want to get to the next and all-important point, which is not visible at this level, symmetries. On top of this mean field kind of physics, we have a very, very rich degree of symmetry, non-obvious in the model. And that's what I would like to explain now, and then we will marry this with this mean field program, and interesting physics ensues from there. So what is this about symmetries? It's a bit crazy if you hear it the first time, but it goes as follows. Take a look at the imaginary time action describing the system. By imaginary time action, I mean just an integral over imaginary time. Here you have the interaction term. All that matters is counting now, fourth order in Majoranas, and then there is this canonical piece sitting here, right? So what we're doing here, we have a time integral, imaginary time. And what you can do, just for the fun of it, you can decide to reparameterize time. You measure time in a different time. Like when you do these integrals we do in the first term, line integrals in classical mechanics, sometimes we show their reparameterization invariant, yeah? So you do just the same here. Instead of working with time, you work with a reparameterized time, and this is a one-to-one mapping. It should be unique and smooth, meaning that this reparameterization is a diffeomorphism from what? From the unit circle onto itself, because this is periodic boundary conditions in imaginary time. So you can do that, right? Now, if you do that and substitute for your fields the time reparameterized fields times a scaling factor, the scaling factor is needed to compensate here what's coming from the measure, you realize that this piece of the action is invariant under this reparameterization. That's an important point now. Is that halfway clear? Yeah. So you have this symmetry, if you want symmetry of this piece. The first term doesn't like this reparameterization, but we agreed for the time being this one is weak compared to that. So what we conclude is that there is an infinite dimensional set of symmetries. Why? Because there are infinitely many reparameterizations, and Maldatzena, who worked on this, dubbed this NCFT1, which is a fashion name for nearly realized, nearly because this one is breaking it, nearly realized conformal symmetry in one dimension. Conformal because the algebra of this diffeomorphism is a classical Virasoro algebra, so you can call it a conformal symmetry. Now, what about this symmetry? You see, it's totally general. I mean, any fourth order interaction and any will always give it to you. So these symmetries are always there, at least provided there are no other players in the Hamiltonian. But normally you cannot buy anything for these. They remain useless. Yeah. But in combination with the mean field program, which we just saw, we get now something interesting from here. So now I marry the symmetry with the mean field analysis from before, and then we see that we have a Goldstone scenario. Yeah. No, I don't. I mean, what I mean is just this Virasoro central charge zero. I mean, yeah, that's it. I mean, all I want to say is we can Taylor expand these functions, and you have infinitely many generators. But if you want to sound educated, you call it conformal. Yeah. I mean, there are various ways. I can give you various answers. For example, if you have fermions, the whole problem, the Hilbert space decomposes into sectors of conserved particle number. You have U1 modes on top of these conformal modes. You have to worry how the U1s talk to the conformals, and all that is born out of the complexity of the Heisenberg algebra compared to the Clifford. That's the best answer. But I would say that 90% of what I'm telling you carries over to the fermions, and I will. But this is maybe it's historic that we just start from this simpler platform here. Good. So symmetry. Yeah. Now, to see how this goes now together, I mean, something interesting emerges. Let's get back to our mean field. That was it. And ask whether this mean field, think of this mean field a bit like a magnetization in a magnet. Yeah, plays a similar role. And you can ask now, how will it change under reparameterizations? And the answer is that reparameterizations, if you just reparameterize time, typically this mean field changes. So it's like if you think of the reparameterizations like a rotation symmetry in a magnet, this is like a magnetization changing under a symmetry. There's a tiny subgroup, these kind of Möbius transformations here. It's a subgroup of the full diffeomorphism group in SL2R, in fact. If you plug this in, you will find that the mean field stays invariant. So this is like rotations around the z-axis. But generic reparameterizations change the mean field. And that means that we should expect a Goldstone mode manifold, which is infinite dimensional. like in a magnet, you have a two-dimensional Goldstone mode. Now we have infinitely many, namely all the parametrizations, the diffeomorphism group factored out SL2R. Yeah? So a non-compact, high-dimensional Goldstone mode manifold. So we run into a classic symmetry breaking scenario. The mean field, which is played by G, changes under these generic ones. It doesn't change under SL2R. And now we know the model is nominally one-dimensional. It's like one time is like one dimension. Yeah? So you have a Goldstone mode in one dimension. And we know that Goldstone modes in low dimensions, and in particular in dimensions 1, become violent at low energy scales. So we should expect that these Goldstone modes are the most important player in the low energy physics of the model. And that turns out to be true. Now, if you think from this basis and ask yourself, what should we do next? If you, again, think about a magnet, then you would want to know what is the action of the Goldstone modes. It's like the Ginzburg-Landau action in a magnet. And what we should expect is that there isn't certain action cost associated to these reparametrizations, and it must come from the explicit symmetry breaking in the model like a magnetic field, and that is this time derivative, which we so far ignored. So the program now is at least conceptually clear. We should take our SYK action, if you want, plug in these reparametrizations, and expand in time derivatives, like in a small magnetic field, and see what we get. And what we then get, by definition, is the Goldstone mode action, like Ginzburg-Landau in a magnet. And here, in this context, the corresponding action is called Liouville quantum mechanics. And that is a very, very simple action which we will get. So, I explain what it is, and from there we can then describe the physics of the system. That's the program. So it's technical, yeah, but I'm skipping over all this. I'm just telling you that there is an exact replica action representation of the Sachdev-Ye-Kitaev system. It looks complicated, never mind what. All I want to emphasize is there is a d by d tau sitting here, and we should stick into this action the reparametrized green function and self-energy and expand. And if we do that, what comes out is an action that must depend on the reparametrizations f, and in particular on time derivatives of these guys. And it turns out that instead of working with these f's, it is more convenient to parameterize them in the following way. You say, it looks weird at first sight, but just accept it at this point. You write f prime equals e to the phi. That's always an option because f prime is uniformly positive. It's a one-to-one map. So it must always be positive, so we can write it as an exponent of something else. And if we do that and ask what it, we find that the Goldstone mode action is given by this relatively simple animal. Yeah? So if you look at that for a sec, you feel reminded of a path integral in quantum mechanics. So it looks like you can forget all I said to you so far. If you would see it in a class, you would say, aha, that looks like a path integral with an imaginary time action of what? Of a massive particle and in an exponential potential. That is what comes out, yeah? And this is, depending on your background, I mean, this is a very famous action. It's, it's called Liouville quantum mechanics in 2 dimensions. It's a one-dimensional version of a 2-dimensional extension, which is called Liouville field theory and was very popular in string theory several decades ago. And there's a lot of knowledge on this beast. I should also add that there is a mass scale, if you want effective mass here, which, if you count dimension, has the dimensions of time. That one comes out as n times n over j, so essentially it's linear in n. This scale is physically very important. It has dimensions time, because at time scales larger than this m, this field, these phis fluctuate wildly. The system is no longer classical. It's full quantum fluctuations. I mean, you have fully exposed quantum fluctuations. Based on power counting, you can see fluctuations go strong then. On shorter scales, this system is nearly classical, and you can do essentially Newtonian mechanics with this. Okay, that's one remark I want to make. And there come 2 more. You should appreciate that this is ultra simple, because, you know, for most practical purposes, an e to the phi potential is like a wall. So the problem has the complexity of a free quantum particle in a half-infinite space. So it looks maybe a bit obscure now, the way I derived it, but what you should appreciate is, take-home message is, the low-energy physics of the SYK is described by a very, very simple problem, which is textbook, just, I mean, semi-infinite wall quantum mechanics. And I'll turn in a second to the results you get from here. And then there's one final point I want to make, that this quantum mechanics is highly universal in the following sense. If you take any quantum mechanics, I mean harmonic oscillator or what, and compute some operator expectation values of p's and q's and at different times, you get functions that depend on time, and depending on the type of operator you pick, you get different power laws or exponential laws or God knows what. Yeah? In Liouville quantum mechanics, the situation is as follows. You take any operator you want, any operator constructed from these fields, local, and correlated with a different operator, time and tau prime, and you always get t minus t prime to the power 3/2. So the 3/2 is a universal signature. No matter which operator you take, it's always 3/2. That has to do here with this exponential nature of the potential at long time scales, large compared to m. And that is at this harmless-looking 3/2 is at the origin of a very high degree of universality in SYK physics. Many correlation functions you get in this business have always the same power law. They are universal. They don't depend on non-universal scales. It comes all from this 3/2 here. Okay. Question?
So I can use one of these operators for the tangent of the original Majorana terminus. So some Majorana terminus.
I'll give you an example in a second, yeah?
Okay, so when how I rate them?
Yeah, yeah, 3/2. Yes?
And another question, so when you go down, so you said that this action in terms of G sigma is sort of valid at low energy?
No, the G sigma is rigorous.
It's irregular.
That is rigorous, yeah.
That can be
That is an exact it's not me, Sachdev it is. That's and that's a rigorous representation, yeah.
When you look at low energy, then you can approximate.
This is the low energy approximation, yeah. And there is an intermediate step, maybe you know, there is a Schwarzian action sitting at intermediate scales, but this is the ultra low energy. I mean, at low time scales large compared to m, or of the order of m. Good. Now let's run a few sanity checks. I mean, of what you can get from there. Ignore this formula. Yeah? All I want to say is, before we looked at the green function, and now we know there are these parametrizations on board. So we should go beyond the mean field level, and what we should do is we should take the mean field result and integrate over these fluctuations. And that looks complicated. It assumes the form of some expectation value. What I want to emphasize is this is like a quantum mechanical quench problem, technically, and you can solve it. So you solve for the green function now, including fluctuations. This is the actual green function. I mean, like the magnetization after you have included Goldstone mode fluctuations, and it looks horrible. But notice here there are some Bessel functions floating around here. This is this half-infinite quantum mechanics sitting there. And you can make sense of it just by plotting this result. So this is now the green function as a function of energy, not of time, of energy. And what you see is that at large energies, large compared to inverse m, we get our mean field result back. So this is the Fourier transform of 1 over square root. So this is what we had before, like in a magnet, high magnetic field pointing up. This is this result. But at low energies, the Goldstone mode fluctuations must go wild. This is essentially the Maman-Wagner theorem. And you get a qualitatively different power law. It's now energy to the 1/2 and not energy to the minus 1/2. And this is in logarithmic units. This is non-logarithmic. So the green function vanishes. And it should vanish because it's like an order parameter in a Goldstone mode setting. So magnetization in low energies gets killed by fluctuations. Same here. The green function gets killed by these fluctuations. And it's the dashed line is the analytics, and the red line is numerics for 24 Majorana fermions. So you see that this is not an artifact. So this is actually, I mean, there are some finite size corrections and so on, but this is pretty much what happens in the system. This green function is important because this green function is the most important Lego block for computing all kinds of observables, yeah? From SYK, which we do now in correlated condensed matter applications and so on. The green function is always the most fundamental one, and so this is why this result is it's methodological, but it's quite important. I'll come back to that in a sec. There is another sanity check you can do. Instead of looking at the green function, you can just look at the partition sum itself, e to the minus beta h traced averaged over this order. And you work and represent this partition sum now as an integral over these low energy fluctuations. And if you work a little bit further still, you can represent this whole package as an integral over energy with an Arrhenius factor. And then there's a prefactor, and this prefactor then is by definition the many-body density of states in the system. Yeah, this is, I mean, if you have an expression like this for a partition sum, this must be the many-body density of state. And this is this red line here, and the numerics is for n equals 34. No? And I mean, and this is so it works down like a charm down to the ground state. So this is really getting this. This is a very strong check for the validity of this Goldstone approach. Yeah? And that is in a way the fundamental aspect of quantum fluctuations in this model, more or less. Now you can ask, what can we do with this beyond working abstract quantities? And this is now kind of an overview of application fields that are currently addressed from this perspective in different communities. So one which I'm personally very fond of, I say a bit more about that in the following, is kind of a Lego approach to correlated quantum matter. So this is a condensed matter angle of applications where you do phenomenology to strongly correlate materials in the following way. You take a material which is strongly interacting fermionic, and you build it from cells, SYK cells, the argument being that these guys are as strongly interacting as it comes, and then you couple them to in ways. I talk a bit more about that in a sec. Let me just mention the second application field, which I will not touch today, and I actually shouldn't touch because I know very little about it, and I don't have sufficient expertise. That's holography. So in holography, the SYK model is considered the one-dimensional boundary of a two-dimensional ADS bulk containing some black hole. Black hole is needed to mimic this chaos physics of this system. And one very interesting question which we are discussing with holographers is what the impact of these strong quantum fluctuations is. Yeah? The strong quantum fluctuations must reflect in the bulk in physics which is not gravitational or classical Einstein-Hilbert-like, but it must be stringy. And so if ever this model has a good will turn out to be a really case for a worked ADS 2CFT1 example, one better understands what the role of these Goldstone fluctuations in the bulk is, and that's an open subject of research. And the third is, I come back to that a little later, is doing quantum many-body chaos in Fock space and probe many-body wave functions and spectra. Now, of these three, in this regime of short times, where condensed matter physics is concerned, this the first one here is kind of interesting, first application. So let me quickly reiterate that. There is now a new approach to phenomenological to strongly correlated matter, which is granular in the sense which I try to outline. You build matter in terms of cells where each cell contains a large but not too large number of degrees of freedom. This n being finite is important because if you send n to infinity from the beginning, it's first of all it's unphysical in a Lego approach, and second you kill all quantum fluctuations from the outset. Yeah, this timescale m goes to infinity. Then you declare your blocks to be asymptotically strongly interacting by design. So that's an assumption of the approach, and the interactions to be maximally atropic. Yeah, and you see where you get. And there are two. Oh, that was from a different conference. There are two kind of applications which we did and which I'm quite fond of. One is looking at really at granular quantum matter in this sense and working out the phase diagram from a lattice extension of this Liouville theory, which I discussed before. And all I want to highlight is that there is a phase diagram emerging. The phase diagram controlled by the coupling strength between these cells. So if this coupling is very weak, this is this coupling strength, then the cells essentially remain isolated and the whole system is like an insulating array. I mean, I'm not explaining this, I'm just telling you, I mean, if you have to be interested. But then it turns out that there is a quantum critical point which is driven by these Goldstone mode fluctuations, by these quantum fluctuations. If you go to stronger coupling, the array turns into a Fermi liquid. So you have an insulator Fermi liquid quantum phase transition. And on top of that, there is a quantum critical regime where the conduction behavior, thermal conduction behavior, it's Majoralas, is strange metallic. So you have a bad metal, strange metal phase. And what's kind of intriguing about this is that this phase diagram, I mean, in particular here, this region looks deceptively similar to what you have in many realistic, strongly correlated materials, like heavy fermions. I don't mention the word cuprates, but in many of those, you have this behavior of a gapped phase and Fermi-liquid phase and strange middle on top. And here you get this from totally cheap phenomenological modeling, yeah? Which may indicate that there is some wisdom in this. But this is, of course, now the holy grail is to find superconductivity in this game. But it's irrelevant. This is like a DMFT kind of thing. So yeah, it's irrelevant in all dimensions. Yeah.
Is this phase diagram somehow the calculation controlled in the same way of the singular granular?
Yeah, it's what
kind of the same
you do, right? You
field plus the fluctuation.
yeah, you start from this Goldstone mode action, actually in the Schwarzian form, and then you do an RG program. So it's RG. What is nice about this is the RG is controlled by very strong consistency. You have to maintain this SL2R invariance at all levels, and that basically gives you the normalizability of this theory. So it gives you a bit of tailwind. You can also do quantum dot physics with that, but I guess in the interest of time I skip that. So get another interesting phase diagram, but I better stop here at this point where short energy scales are concerned, short time scales and large energy scales. And now I turn to the long time regime. It's now a totally different story. Same model, but methodologically, conceptually really different. I mentioned in the beginning, we don't know but understand the connection between these very well. And we have different symmetries. You can forget now the conformal symmetry and a different approach. Yeah? So now we are here at these at long scales. And first of all, some numerical observation. If you do numerics, and what do I mean by numerics? In this long time regime, you are primarily interested in the fine structures of the many-body spectrum of the system. Yeah? So you can take a computer and you run the usual diagnostic tests in quantum chaos. Let me emphasize this first one. The first one is the probability to find some close-by levels as a function of the level spacing measured in units of the average level spacing. So you have an average level spacing, S is energy separation in units of this average one, dimensionless. And note that the P of S, the probability to find some levels close by, goes to 0. And that means you have level repulsion. But not only that, I mean, so levels repel. They repel in almost perfect agreement to the predictions of phenomenological random matrix theory. Yeah, so you can mimic this behavior by just a stupid Gaussian distributed Hamiltonian, and that is the usual indication of hardcore quantum chaos in the system. The system becomes fully universal, fully ergodic. In case you haven't seen that, let me show. This is the usual graph one shows in these occasions. So these are a few other chaotic systems with their P of S spacing distribution, and they all agree to the predictions of random matrix theory, this random matrix universality, and SYK is no exception. It shows this behavior. Yeah. Now, if you look closer, you find that at slightly larger energies, there is not only this RMT asymptotic, but there is also corrections to RMT, deviations, which are systematic and universal. And this is where the interesting physics is. The random matrix limit itself at the smallest energy scales is, well, we take that for granted. But what's more important are deviations from RMT, because they tell you about the actual physical processes that ultimately stabilize this random matrix ergodicity. And let me mention two of these. So what this here is, these are the fluctuations in the number of levels in a certain width of dimensionless width of L, and details are not important. What I want to emphasize is that the blue line is random matrix prediction, and the red and green are SYK for different numbers of n. And you see here, these deviations are not numerical junk here, they are real. And same here, this is the Fourier transform of the spectral two-point function. Another correlation function, this kink-like thing here, this is what RMT does, this here. But this upturn is not RMT and the minimum. So there is non-universal physics sitting here, and we would like to understand this. So this is a benchmark test for our understanding of the model. Yeah? Hmm? Very good. The kink is at times of the inverse order of the many-body level spacing. So it's 2 to the minus n. And this here is a subject of debate. It's order n times larger. People debate whether it's n or log n larger, but right. This is numerics. Yeah. And now I want to understand this analytically. Right. So the goal is to understand these results. Yeah. Here. Yeah, I didn't explain very well because it's not so important to me. It's just, but let me explain. So you take a window in energy of a certain width, call it L. L is dimensionless in units of the mean level spacing, and you count the number of levels in it. And then you ask from one realization of the other, what are the fluctuations, or what is the variance? And for uncorrelated levels, you would expect Poissonian statistics, so you would expect a square root of width increase. The thing about random matrix theory is that this increases only logarithmically, so the spectra are very stiff. There are very few fluctuations. And that's why this is remarkable, because this is actually a quadratic increase, so you have super Poissonian fluctuations in this game, and that's where SYK physics comes in. Yeah, and we want to understand this. Yeah, very good. Okay, so now how can we approach this problem? And so these are the, yeah. One should compute some diagnostic correlation function. The usual correlation function you compute to describe all these phenomena is this so-called spectral two-point function. Many body density of states at a certain energy, correlated with many body density of states at a slightly different energy, averaged over this order. Yeah? So that is the test observable. And we want to compute this now. And what we do is we do an approach which at first sight looks downright stupid. I mean, this is an as many body problem as it comes, yeah? And we approach it from the problem of first quantized quantum mechanics. So we interpret this Hamiltonian now, simply the SYK Hamiltonian, as a big matrix. And if you think about the definition of this matrix, it's hellishly complicated because it's a full many-body Hamiltonian represented as an exponentially large matrix. And you can understand that the disorder, which is sitting in the matrix element, there are only algebraically few disorder matrix elements in an exponentially big matrix. So the matrix is sparse and massively correlated. So it's as unpleasant as they come. Yeah? Still, one tries to push this. And I mean, to make no secret, what gives one tailwind is this Majorana commutation relations, which sit in the background, so which allow one actually to make progress in this way. Once we accept this, then the density of states and related observables are contained in the resolvent, when this is a high-dimensional many-body Hamiltonian. And we can now apply methods borrowed from the physics of single-particle random disorder problems, where everybody computes resolvents, and try to import them here. Yeah, so that is the strategy. And once one does this, one immediately runs into another type of symmetry breaking scenario, which is different from what we had before. Let me briefly outline the idea here. So we agreed that these are our observables of interest, and we need retarded and advanced Green functions. Yeah? So we can write them as a matrix structure like this. And notice that this beast has a continuous symmetry. It is, because its I delta is infinitesimal, you have an invariance under U2 rotations. You can rotate in this space. It's only symmetry breaking is infinitesimally small as this here. And this is a causal kind of symmetry. So it's an infinitesimal breaking of causal symmetry, if you want. Physically, what does the Green function describe? It describes propagation in Fock space. This is many-body. Yeah? In Fock space, between Fock space sites m and n. So it describes this kind of scattering. And here these little dashed lines indicate scattering of the SYK interaction Hamiltonian. Yeah? So it's ultra formal, you understand. There is nothing built in yet. It's just a bit of syntax. Now, one thing we anticipate is that once we consider the Green function averaged over this order, the averaged one, our causal symmetry gets broken. Why is that? Because like in a single particle random problem, once you average over realizations of the disorder, the propagator picks up an imaginary damping time. This is just a damping of amplitudes due to scattering of disorder. So this I delta gets upgraded to a finite 1 over scattering time, plus here and minus here. So the U2 symmetry gets broken by disorder averaging, and it's a spontaneous breaking. Spontaneous breaking. So we get another, we now have another coset space Goldstone manifold. I mean, the disorder average propagator can be represented like here. The symmetry is, gets broken down to U1 times U1. So you have a Goldstone mode due to a different type of symmetry now, which is U2 over U1 times U1. And so this is, we get on very general grounds in any random medium, so more or less for free. And there must again be now some effective Goldstone mode action which describes the fluctuations under these Goldstone modes. And for single particle random problems, these field theories, Goldstone mode field theories, were derived in the early 80s by Wegner and Yefedov and other people in single particle context. And it turns out that you can now construct a very similar, I mean philosophically similar, structurally somewhat different Goldstone mode action in this context, and you can work it out in closed form if you use the commutation relations of the Hamiltonian, which in turn are defined by those of the Majoranas. I'm not describing how, but it's not terribly complicated. It's also, I mean, somewhere intermediate complicated. But the point to stress is that the Majorana computation relations are again crucial here. So now the next thing is to read out information from this field theory, and I will not go into any degree of detail. I just want to show you some results. I mean, to show that this is an analytic approach, and it's the only analytic approach to many-body quantum chaos that in any system that I know. Yeah? So it's a kind of good thing to have. One thing we can do is we compute now this spectral two-point function, which I mentioned in the beginning, and get some closed formula. I mean, here it is. Doesn't tell you very much. I mean, you can just look at it. But we can plot it again. We compute from here the level number variance fluctuations. This is the observable which I showed before. So that beast, and this is the same function predicted from this formula here. And the agreement between right and left is perfect. So there is parameter-free agreement down to the percent level. This has been numerically checked. So we get a perfect understanding of these superposonian fluctuations from the theory. And I'll tell you in a second what the intuition behind it is. It's actually trivial, the intuition, but still there is some intuition. And that is, again, a sanity check that this approach works. Here's another one. This is the spectral form factor, this other thing I showed where we had this upturn. And this is the result from the field theory calculation. And the agreement here is a bit more tricky because this is extremely ultraviolet, but I think it's still very much okayish. I mean, so and certainly semi-quantitatively, you get this minima and the upturn. And you can push this further. If you really look into the spectral form factor, in detail, you see here this. Let me show you here these cusps, yeah, and this little looks a bit like junk, but it's not junk. So these fine structures here have to do with the symmetry of the model, and if you compare this with the analytics really fully resolves these fine structures. So the approach just works. That's what I want to say. So we have this under control, and now again we can ask what can we do with that besides testing these numerical results for SYK. Before I tell you what to do with, let me give you some intuition for this, or the explanation for these strong fluctuations in the system. That was actually qualitatively understood some time ago in nuclear physics and related fields. The thing is as follows: if you take a normal one-body quantum chaos problem, and you look at the spectrum, disordered electron or billiard or God knows what, spectra usually look as follows. You plot the density of states as a function of energy. You usually obtain hard edges. So maybe with some tiny tiny non-perturbative tails here of the scale of the level spacing, but usually spectra are very, very hard. If you look at a many-body spectrum, density of states, you take a real nucleus or something like that, average spectra tend to be very, very soft, Gaussian typically. And this is precisely a consequence of the fact that in a one-body random problem, you usually have as many random matrix elements as your Hilbert space has dimensions. So you have a lot of randomness in the problem. In a many-body problem, you have very, very little randomness. And if you turn one knob in your Hamiltonian, you have only algebraically few, exponentially many of your matrix elements change. And that is a very potent source of fluctuations. So the spectra become very, very soft. They show collective large-scale fluctuations, which manifest by this slack Gaussian density of states. And this is also the origin for the super-Poissonian fluctuations in level numbers in certain strips. Yeah, so this is the intuition behind it. Yes, and so we can understand this. And now we can again ask what is it useful for? Here the thing to emphasize is now really the study of many-body chaos in Fock spaces. I mean, this is this application line. And I just want to give you the idea of where this is going. Probably many of you, if not all, have heard of many-body localization, a phenomenon very popular in quant-mat and chaos and not perfectly well understood. So much like in this condensed matter modeling, the SYK Fock space is a Lego brick of MBL. Yeah? It's a spatially non-extended system, but it has full many-body chaos. It has a fully developed many-body Fock space, which has the topology of a hypercube. And we have localization, delocalization transitions in this space, which can be driven by certain parameters. But this is a system which we understand now analytically. So the I think, a promising direction to go into, this is not fully developed, is to study MBL from this perspective. Yeah? We're just at the beginning. But let me just flash one view graph. What you see here is the following. We here consider an SYK model perturbed by some diagonal contributions in Fock space, some additional, beyond the plain vanilla SYK, we added strong perturbation to the SYK, and a perturbation of such type that it wants to localize in Fock space. So if we make this perturbation very, very strong, we get localization, and this is shown here in cryptic ways in the inset. If we make it very, very strong, we get a crossover of spectral statistics from Wigner-Dyson random matrix, which I showed before, to Poissonian. So localization, delocalization transition in Fock space. And it shows in the statistics of many-body wave functions, in particular in the so-called inverse participation ratio. That is the normal diagnostic you run in MBL to tell localizing phases apart from delocalized phases. And same here, so there is this transition sitting here. And we now have a very good understanding. So the black line is the analytic result from the field theory, and the crosses are direct diagonalization. Here it should all end. Here we run out of control in the analytic approach. We understand why. What's interesting is that there is a phase, the dashed green line is encoded units is random matrix theory. And there are systematic deviations here. And for the expert, this is the trace of the non-ergodic extended phase. In this context, so one can understand the structure as well. So, yeah, from my perspective, that is a direction to go into now. To use this as leverage for MBL physics, but it's the next chapter. I think, yeah, I'm pushing my time. Good point to conclude. I hope I could convince you that this is a fun or rewarding paradigm of many-body chaos, and there is a full-fledged spectrum of results there, exponential instabilities, fluctuations, and God knows what. And we have it, this is a bit like a harmonic oscillator in this field now. Yeah? You can work with this, and if you want to study it, you can go into there. One thing which is a mystery subject, but it's now, there's quite a few groups in particle physics and string theory working on that, is what all this means in holography. And I think we have a social phenomenon here. We have people like me and others who understand the quant perspective of it very well, but have no clue of holography, and vice versa. So this is a good opportunity to do some interdisciplinary stuff. And anyway, yeah, with that, I think I should stop. Thank you.
Could you give us some intuitive understanding for this French metal phase that you obtained in your phase diagram?
Yes. Yeah. Yeah.
So it was for the conductivity, thermal conductivity, I guess?
Yes. Yeah. The intuition is very simple. I remember in the beginning we had this green function 1 over square root. Yeah? So if you just assume this and you probe thermal conductivity, you have strange metal behavior. It's a non-Fermi liquid phase, so that is a strange metallic one. In a way, it's simple. This comes out here very simply. Now, suppose you lower temperature, yeah, in this array. Now the SYK grain realizes it's not alone in the universe. It's tunnel coupled to nearest neighbors, and this tunnel coupling is a relevant perturbation. So it becomes stronger and stronger, and at some point it becomes so strong that the SYK guys all talk to each other, and then the non-Fermi liquid gets destabilized, and you cross over, not phase transition, you cross over into a Fermi liquid. Okay. So that is a strange metal. You know, at high temperatures where the grains are asymptotically isolated, we shouldn't expect any Fermi liquid behavior because the reference point is strongly non-Fermi liquid. Now, the job of the Goldstone mode fluctuations is to fight with this tunnel coupling. The Goldstone mode fluctuations, if the tunnel coupling is initially too weak, the fluctuations kill the coupling. So you have a battle going on between these quantum fluctuations and the coupling, and that then gives you this quantum critical.
Okay. So when you say when you have this square root of t,
yes,
function of square root of
yeah,
it's not the usual picture we have for magnetized Fermi liquid or strange metal. So it's not the self energy of the Green's function at all, which carries the Green's function itself.
the Greek, yeah, but because here's not exactly. It's it's this paradigm shift that you start with a model where interactions are so bloody strong that they become simple. I mean, it's just this. Yeah, one can believe in it or not. I mean,
yeah, 2 questions. One is related to the your intuitive argument to refer to super-Newtonian statistics.
yeah.
I understand the fact that any many-body problem is completely peaked and Gaussian shaped,
Yes.
and that wave function of different energy, when you go too far, they live in different shells, and there's monodol. So I use the spectral to Poisson. So why super Poisson?
Yeah, exactly. That
or just a typical of SYK?
No, I think that's general.
So
I think, well, not people have been knowing this for ages in nuclei.
Okay.
Nuclei show this. I couldn't vouch for our beloved MBL systems, but if you take I think I would go as far to say that if you take a many-body system which is spatially structureless, ergodic, and really many-body in this sense, this is generic.
Okay.
And what we usually have is not generic.
And the second question is, when you do the sigma model approach, in order to find the spectral correlator R, when you do the Sachdev point, you assume that there are no loops, like a tree-like structure in the space, or no?
No, it's no assumption. No. That's. Thank you for the question. I claimed that this Majorana blah 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 makes it all very simple. It's exactly this point. When you fluctuate around there is one zero mode which is non-perturbative, but then there are lots of massive fluctuation, and at this level the theory is Gaussian. So this is the consequence.
If you try to do it for just fermions, like a spin chain, then you do it to Fock space, then you have
exactly. Then it's
you do the sigma model, but you don't.
Yeah. Then it's getting actually. Chris Laumann wanted to go into that. I mean, there are these mini loops, and you know this much better than me, but precisely. But so this is where the simplistic nature of this model sticks. Yeah.
I have one question. So related to this, you mentioned this causal symmetry breaking, right?
Yeah. It's just.
Is there physical consonance with that? So I mean, you really lose causality, or
Nah, that is.
because at the end of the day, I guess
just
even with an imaginary
truth
part, you're still.
Truth be told, I just needed a name to stick on it because it's really very different from. But there are physical consequences. I mean, if you, for example, these Goldstone modes, which you get from there, in a normal metal, they give you are the diffusion modes. Yeah, I mean, so here these Goldstone modes are relaxation modes in Fock space. They're analog of diffusion modes. But the mechanism is precisely the same. So in the 80s, people made deservedly a big fuss about that. And it's always this, and I call it causal because you just upgrade this I delta to something finite. This causality
but the two blocks state, the two retarded in advance remain causal. In the sense
Yeah. No. Yes.
Not that you spoil
No, it's
that
not like
kind of
this. You can also do this. This was then the analog of replica symmetry breaking, which is, but that's a different story.
Okay, wait.
So this connected cell of this SYK model, what kind of physical system that you have in mind for doing this kind of problem?
Well, these granular things?
No, these arrays of SYK model, they
Arrays.
are connected.
Non-specific. I mean, there are papers from, I can point to them, Leon Berlens and Eris Bergen. So they believe that this modeling is really relevant for heavy fermion materials. I'm not a strongly correlated person, but I think it's fair to say this is all totally uncontrolled belief. Yeah? You just see how far you get. It's really phenomenology in the sense of the word. Yeah.
Monica, you had the question.
Yeah, sorry, to follow up on this question, actually, maybe I don't know, but what was this original quote-unquote causal symmetry that you were breaking?
No, it's something totally simple. It just sounds mysterious. If you want to know green functions, you have a retarded in advance, and they're almost the same. They just differ by I delta. Yeah. In this business, you start by representing these green functions as a Gaussian integral, replica or supersymmetric Gaussian integral. Now, if you stare at your Gaussian integral, the Gaussian kernels of these two guys are almost identical. So that means that you can continuously rotate your integration variables. They have a fully exposed U2 symmetry. I know what the breaking of this symmetry is. And the breaking of this symmetry is irreversibility, which shows in that the Goldstone modes are diffusion modes. Now, that's what it is. I mean, the breaking of the symmetry leads to diffusive dynamics in a metal, and here it leads to the analog of this in Fock space. So that indeed has strong physics. And by the way, if you go then to in low dimensions, 2 dimensions to very long scales, the symmetry gets resurrected, and that is the physics of Anderson localization. So in the 2. Yeah, so there is some physics attached to them, yeah.
Any other questions? If not, let's thank Alex.